amplitude as x, whatever that A is, it's always going to be the maximum displacement from our equilibrium point. Okay? So at our amplitudes, all I have is 1/2 Ka squared. What does this say about the relationship between the amount of energy in a simple harmonic oscillator and the amplitude of the oscillation? What does this say about the relationship between the amount of energy and the amplitude?
They're directly linked.
They are directly linked, but you need to be a little bit more specific in this case. If I double the amplitude, what do I do to the amount of energy?
Double. Quadruple.
Why?
Because it's squared.
You square the amplitude, right? If I double the amplitude, what do I do to the amount of energy? I square it, okay? If I'm in an earthquake, okay, this is hugely important because if I double the amount of the wave, what do I do to the amount of energy that that earthquake has? I quadruple it, okay? That's pretty important for people in an earthquake zone. Oh, wait. We're in an earthquake zone, aren't we?
That's fake.
You know, I think you're right. I don't believe it either.
That's just that butthole.
Yeah,
back.
just
That's
wait. Tonight.
That 8 level comes,
Yeah.
destroys everything.
Okay. Total energy is directly proportional to the square of the amplitude. Okay? Also, we can look at the equilibrium point. At the equilibrium point, all of the energy is kinetic, right? Therefore, this is the maximum velocity point. Anywhere else on here, I'm not going to have all of my energy being kinetic energy, so my velocity can't be at my maximum. That's how I know that this is my maximum velocity point, because all of my energy is kinetic at that point. What?
Dun, dun, dun.
Hang on.
So now we go to A, B, C, C, A.
We gotta pull up oscillations too.
That's 3.
Well, that's what we're on, so.
Oh. Well, he said oscillations to average. I don't know. Oh, it's called oscillations 2. It's 3.
It's the second page.
I get what you're talking about.
Shush.
From the energy equation, we can create velocity formulas as a function of displacement. For a given elastic material, velocity depends only on position. Let's see. For a given elastic material, velocity depends only on position. As total energy equals amount of energy at either maximum, we can set general equations for both components of energy equal to the total potential energy. What do I mean by that? Here's kinetic energy, and at the end, at the amplitude, where it's all potential energy, I can say that since that's all my energy, I can set 1/2 mv squared plus 1/2 kx squared equal to 1/2 ka squared. And now I can relate my velocity to the position.
So it's Ka squared, energy, total energy.
Yes, that's total energy. Why is that total energy? Because it's the potential energy at the amplitude, right? And it's all potential energy. Okay? Energy at either amplitude is total energy. So why not just set these two equal to 1/2 Ka squared? Okay? Now, I want to find a velocity formula. I want to find a formula that tells me what my velocity is at a given point. Why would I want to do that?
Because.
Isn't that how we characterize motion in general? We try to find its velocity at certain points. Okay? So that's something that we do to characterize motion in general. Find its velocity. Okay? So if I isolate, right, I'm going to have to get rid of the 1/2. That goes away. Well, it will go away. And then I'm going to subtract 1/2 kx squared from 1/2 Ka squared. I'm going to divide by m, and then I'm going to end up taking the square root of that. Really? So
And I want you to
I can factor it. Oh, that helps, doesn't it? Because what does this give me?
oh, we
An
can
equation.
factor the A out as well.
Uh-huh, we factored the A out as well. This gives me a difference in squares, doesn't it? A squared, no, I didn't factor the A out.
Yeah, you did.
If I factored the A out, wouldn't it be out here?
Yes.
Well, on the next step, you factor it out.
Oh, I'm not on the next step yet. You're way ahead of me.
You even put a question mark there because you don't know.
Yeah.
I have no idea.
You'll see why in a minute. It helps us. Okay? But this is one of those weird things that some brainiac mathematician, you know, a zillion years ago did because he knew what was going to happen. You know, no. I could never do that, right? I could never anticipate that something was going to help me out. Huh? This is cool stuff.
Well, that's a matter of perception.
It is, isn't it? Okay, so factor the A out, okay? And when I do that, I have to put the x squared over a squared, right? Okay, so I factored the A out, and I did this. And we know that at maximum displacements, total energy equals 1/2 kx squared, or Ka squared, and at x0, total energy equals 1/2 mv squared. So we can set those two equations equal to each other. What do I mean by that? I can set those two equal to each other, right? At V max, 1/2 mv max squared equals 1/2 Ka squared. And I can isolate V max from this. So I've gone off on a little tangent here. And I've said that,
Oh, wow.
let's see what I did. I multiplied by 2, or I got rid of the halves, and then I divided by m, and then I took the square root of that. So you would agree that V max, my maximum velocity, equals the spring constant over the mass times a squared. Okay? Or I could take the A out, and now we can go back to the other equation. This gives us a way to find the maximum velocity of a mass if we know the elastic constant, in other words, K, the mass of the oscillating object and the amplitude of the oscillation. But I seem to have taken a divergence away from this. We'll get back to it here in just a second. Oh, does something here look familiar to something there?
Yeah. Kind of a lot.
It's
Okay,
because it's
let's
not
see
a
what we can
square
do
root.
with that.
You just took the square from the velocity.
Yeah,
moved it over there.
notice that V max squared also equals Km over A squared. Why can't I just put V max into here? since, or Vmax squared, why can't I put that into there? So that's why I took that little divergence, and that's why we factored the a squared out. Because I wanted to be able to substitute Vmax into there. Now, obviously recognize someone far smarter than me figured this out. Someone had to teach me this. And so V squared equals Vmax squared. Does it make sense that my velocity somewhere along this path, say here, is going to equal some part of my maximum velocity? Okay, here's where my maximum velocity is, right? Does it make sense that the velocity here is going to equal some part of that velocity? Well, what part of that velocity does it equal? It equals 1 minus x squared over a squared. And you can think of x squared as being this far towards the amplitude. X squared is this far towards the amplitude. And if I subtract that from 1, I get what the velocity actually is. Okay? So if I isolate V, I now know that my actual velocity anywhere on here, which is what I wanted. I want to analyze the motion of this. The velocity anywhere on here equals this amount of Vx. So the velocity anywhere along here equals this amount of the Vx. And you can see that since this is 1 minus something, that value is always, well, this value is always going to be less than 1, isn't it? X squared over a squared is always going to be less than 1 because x squared's here and a squared's here. So this whole value is always going to be less than 1. So it's almost like multiplying Vmax by some kind of a percentage. Okay? So my velocity anywhere along here is going to equal my maximum velocity times some kind of a factor that's part of 1. Okay? This gives us an equation to find the velocity at any displacement if we know the maximum velocity and amplitude. So I have a way to find maximum velocity. Okay, it's going to be the square root of k over m times the amplitude. And I have a way to find a velocity anywhere if I know the maximum velocity and the amplitude. So let's do a problem and then we'll stop. Okay. The spring stretches 0.15 meters when a 300 kilogram mass is gently suspended from it. Why would I do that? Why would I suspend a spring or a mass from a spring and then just set it up horizontally? What am I probably trying to find with that? Yeah, I'm ultimately trying to find the spring constant, right? Okay. So the spring is then set up horizontally with the 0.3 kilogram mass resting on a frictionless table. The mass is pulled so that the spring is stretched 100 meters. Wow, that's a long spring. 100 meters from equilibrium and released from rest. That's going to hurt someone, isn't it?
It's 0.1.
Is it?
Yeah.
Oh. My point is over there. Okay.
Wait, can we do it as 100, please? Just like pretend.
Just times it by 100.